Okay, so for Calculus Chapter 2, number 46, um, you're given the height of some object as a function, and you want to figure out something about its speed. So the speed is basically velocity for our purposes. So what this question is asking here is this right here is our position function. Whoa, sorry, it's writing all over the place. I want to erase. There we go. Position function. And we learned that if you take the slope of a position function, that you actually get a velocity. So slope of position gives velocity. So in this case, I'm not looking for an average velocity. I'm looking for a velocity at exactly t equals 2. So what I want is an instantaneous velocity. If it was an average velocity, that means average slope, essentially, so slope of a secant line. Instantaneous velocity should make us think slope of the tangent line at t equals 2. Or another way of thinking about it is instantaneous rate of change at t equals 2. And these things, the tangent line and the instantaneous rate of change, are referring to for h of t. They're referring to our original function, the position function. Okay, so let's look at this. So velocity at t equals 2 is going to be the slope of this thing's tangent line at 2. So in order to figure out its tangent line at 2, we're going to take the slope of a line through 2 and something close to 2. So I'll say h of 2 plus a little bit. So normally we use h, but I can't use h here because it's already used, so I'm going to say k. So h of 2 plus a little bit minus h of 2 all over 2 plus a little bit minus 2. So if you wanted to think about it, the h of t is this parabola that's upside down. And let's say 2 seconds is about here, t equals 2. So that's 2 h of 2. So then what we're doing is we're picking a point close to it, calling it 2 plus a little bit, h of 2 plus a little bit, and then finding the slope of the line through those two. But really what I want is just the slope at 2. So I'm going to move this point closer and closer that way, and the way to write that is to say let k go to 0 using a limit. Okay, and remember this bottom is always going to turn into just a single variable k at the bottom. Normally it's an h, but since h is taken, we're writing k. So then let's work this out. So limit as k goes to 0. Now h is 100 minus 4.9 t squared. So this is going to be 100 minus 4.9 2 plus k squared. So that's the first term. And then minus 100 minus 4.9 2 squared. All over k. So if we work this out a little bit, let's see what we get. Limit as k goes to 0 of, let's see, these 100 minus 100, that'll cancel. And then I can get, let's go, negative 4.9 parentheses, that'll be 4 plus 4k plus k squared minus 4.9, or sorry, plus, because it's a negative negative, 4.9 times 4. And then this 4.9 times 4 and that 4.9 times 4 will cancel each other out. So if I simplify a little bit more, I'm going to get negative 4.9 4k plus k squared all over k. Now I can factor out a k. So negative 4.9 times k, parentheses, 4 plus k, that's a k here, all over k. And then these k's will cancel cancel, and cancel. And so what I'm left with now is the limit as k goes to 0 of negative 4.9 4 plus k. And when k is 0, or goes to 0, this goes to 4.9 times 4, which is negative 19.6. In this problem, the height is given in meters, and we're looking in terms of time, which is seconds. So height here is in meters. Time is in seconds. So my slope is change in y over change in x. It's meters per second. So my units here are meters per second. Okay. And why is it negative? Well, it's falling downwards. So in that sense, the way that we've set this up, downwards means negative velocity. So it's falling at 19.6 meters per second downwards. Okay. All right. Hope that helps.